Hello everyone, welcome to another video on conjugate view method. Today we'll be looking at another question. In the previous ones we have solved, it is the case of having a particular load on a beam. Where you have a point load, only the point load on the beam, or you have UDL on the beam. But in this question, we have a UDL, that is uniformly distributed load, and a point load at the same time on a beam. So we want to find the rotation at B and Y at B. So for you to draw this, or for you to get the rotation and deflection at B, what we will do is this: we will separate the loading. That means I will have the UDL separate, calculate the reaction, and draw the bending moment diagram, and separate the point load, and also draw the M/EI diagram. The reason being that when you want to plot the bending moment diagram of this beam together, it's just a sketch. The points we will get the bending moment will not tell us actually how the bending moment diagram will look like, or the curve or the shape it will take. So there are some cases plotting them together will actually make sense, but there are some cases, like this particular one now, if you plot them together, it takes an experience for you to know how the curve or the shape it will give you. But I will advise, the method I vibe in is separating them, do them separate, and then calculate separate, and add my answers together. So as we go on in the video, you will see the method. Like I said again, the method is the reason I love this method is, since you can't tell how the shape will look like of the bending moments, and when you do them separate, you won't have problem drawing the bending moment diagram. So let's do it. So summation of moments at A equals to 0. We have look at MA plus 50 times 4 multiplied by 2. So when we evaluate this, we arrive at MA is equal to 400 kN/m. And we take summation of forces in the y direction equals to 0. We have VA minus 50 multiplied by 4 equals to 0. Our VA is equals to 200 kN/m. So we have gotten the support reactions. The next point is to calculate the bending moments at point A, the midpoint, and the free end. And you know that the moment at the free end, which is at point B, will be 0. So MD at 0 at B is equal to 0 because it is the free end. Then we have already that our MA is equal to negative 400 kN/m. So the negative being that when we try to calculate the reaction, the assumption was in the anti-clockwise direction. So, and we arrived as positive for the answer, which says that our assumption is correct, a negative bending, and that is where this negative came in. Then the bending moment at midpoint, negative moment at midpoint, will be equals to this MA, which is negative MA, then we have the RA, which is positive RA multiplied by the perpendicular distance, which is 2, and also the UDL minus 15 by 2 by 1. So the MA is negative, the RA we go in the clockwise direction, and the point load, the UDL, we also go in anti-clockwise direction. So we have this to be minus 400 and when 200 multiplied by 2 minus 100. You evaluate this, you have that this is equals to minus 100. So we have gotten the points for this UDL. Next is for me to draw the bending moment. So at MA we have this to be 400. So we have 400 over EI. Then at the midpoint we have this to be 100 over EI. And we have this to be 0 here. So it's going to be this manner. So it is a negative bending. Then we turn it to a conjugate beam. The fixed support becomes the free end, while the free end becomes the fixed support. This is point B and this is point A. The next step is to drop that of the point load. So half this 200 this A B. So we take summation of moments at A equals to 0, then negative MA plus 200 multiplied by 2 equals to 0. MA is equals to 400 kN. So we take the summation of forces in the backward direction. So VA minus 200 equals to 0. Therefore VA equals to 200 kN. So we have gotten the reactions for the point load. So we draw the M over AI diagram for this point load. Okay. So we need to get the moment at this point and also at this point. And we have the MA equals negative 400 kN and MB equals to 0. So we have to calculate the bending moment at the midpoint. This is equals to, so we have negative MA plus VA 2 the MA goes in anti-clockwise direction, then the VA goes in the clockwise direction. Then I'm looking for the bending moments at the midpoint here. Remember that this loading is at this midpoint. So since I'm looking for the bending moment at that point, that is the point of section, and any load at that point will be removed. And that is why the 200 kilonewton is not included in the calculation. So my VA is 400, my MA is 400, and my VA is 200. So we have negative 400 plus 200 multiplied by 2. And when you evaluate that, you have this to be 0. Now, gotten the points. Let's see for us to draw the MO by diagram for this guy. This is the midpoint. This is point A. This is point B. So we have that of the A should be 400. And at the midpoint should be also be 0. Then so this is negative also. Turn this to a conjugate beam. This the free end and this one to the cantilever. Since it's a negative pending, it goes upward. And also this will also go upwards, being a negative pending. Is for us to calculate the rotation at B. So what I will do is this. I will calculate the rotation at B in this diagram, and also calculate the rotation at B in this diagram, and sum them together. So the summation will give us the rotation at point B. And the rotations are the shear force at that point. So theta B is equal to theta B1 plus theta B2. The rotation at the first diagram plus the rotation at the second diagram will give you the actual rotation at B. So rotation B1 equals to will be the area of this shape, because this goes down to point B. There is no reaction at this point. So the area of this is given by 1/3 of BH, which is this. The distance is 4. When you simplify this, you have that rotation B1 is equal to this. The next is to get rotation B2. Which will equal to the area of this shape. And remember that here we don't have any shape here. So the shear force at this point will be 0. So we are going to take only this point. And we'll have this of the triangle. When you simplify all this, you see that theta B2 is this. So the actual rotation at B will be the addition of these two. If you add all this together, you have that the actual rotation at B is, if we calculate the deflection at point B by calculating the moment at this point from this conjugate beam plus it by the bending moment at this point. So the actual deflection at B is equal to deflection of B1 plus B2. So this is the B1. This is the B1. So I'll get the moment at this point, which is the area of this multiplied by the centroid will give me the deflection at point B. That is B1. Then B2 will be area of this multiplied by the centroid. And deflection, while B is equals to the area of this man, of this shape, multiplied by the centroid. When you evaluate that, you have this to be the YB. So the actual deflection at B will be the addition of YB1, YB2 will give you the actual. So this, when you add them together, you have that this is your YB.